you know Sebastiano. He will talk about his master thesis titled Two Arms, One Goal, that concerned itself, or Sebastiano worked on two-arm parcel manipulation the last 6 months.
Okay. Hello everybody, and welcome to my master thesis entitled Two Arms, One Goal, Learning Dual Robot Manipulation for Material Handling with Online Reinforcement Learning. In modern industrial environments, the ability to automate complex manipulation tasks is crucial. For example, if we want to perform some tasks that are grasping, lifting, or positioning objects. And in particular, robotics can help to improve the efficiency and the speed of those processes. And normally in normal environment, people adopt a model-based controller to move the object in the scene. But the problem of grasping a box is not that simple to solve, because in the real world we can we have to face and to manipulate objects that have real world characteristics. So they have holes, they have tape on the top of it, and so it is hard to achieve a policy using robots that allow to manipulate those boxes. Even if we just want to grasp them, it can be pretty hard because of the real world characteristics that we can find on these boxes. So what happened is that people try to implement imitation learning and reinforcement learning approaches to solve this problem. But this is not actually very easy to solve. I can show you some example here. So the one that you see here on the top right corner, it works pretty well, but it's actually teleoperated. So there is a human in behind moving the robot to accomplish the task, and it's not autonomous. The other two examples that you can see here are one solved with imitation learning and the other one using reinforcement learning. But the one on the left, as you can see, it's sped up 9 times, so it's not actually implementable in the real world. And this one was just trained in simulation to lift a box of this size. So achieving a real world transfer of those policies to manipulate objects is not that easy. For this thesis, what we want to do is that we want to study this problem of manipulating boxes, and in particular we want to compare the performances of dual robotic system actuated with suction cups using model-based controller, that in my case was just a period tree, with the performances of learning-based method that can be trained using, for example, soft actor critic or reinforcement learning with prior data. And the reason why we want to use two robots is because using two robots to basically improve the speed and the efficiency of completing the same task just using one robot arm. In particular, we focused on tasks that can be useful in logistics centers, so when we have to manipulate boxes or parcels, and I selected to train policies that can lift objects, that can rotate objects, or combine these two motion, like this one, so you can lift and rotate it at the same time. And then we train another policy to move an object to a predefined position in the space. Okay, the framework that I used is based on SERL. SERL stands for Sampling Efficient Reinforcement Learning, and it's a public repository where people implemented several algorithms to train agents online to perform several tasks. So how it works is that you can record demonstration of the task that you want to accomplish, and then use some algorithm that are implemented there to train the robots to perform the task that you want. So for example, you can train a policy that can lift some small objects. You can also train policies for two robot arms to, for example, assemble an IKEA furniture, or to perform these other two tasks that you can see in the bottom. And the good thing is that SERL also allows to introduce visual augmentation, so you can directly feed into the neural networks the data coming from RGB images, depth images, or even point cloud. And so just to sum up, for my thesis, what I was doing and what the procedure that I adopted was to first collect some human expert demonstration of the task that I wanted to accomplish. Then I train the actor and the critic network in order to complete the task that I wanted. And then I deploy the policy that we achieved in the real world. And in particular for the training, I had to use some more advanced techniques, for example, that I will explain briefly. But what I was using was point cloud data augmentation, the human in the loop, that is a concept that I will explain in the next slides. And then for the last task, so the one of moving a box to a defined position in the space, I introduced insight experience replay and residual reinforcement learning. So the first thing, as I said in Searle, people can use visual augmentation, and in particular how it works is very simple. So we have those camera on the wrist of the robot arm, and we can use those camera to visualize the local the proximity of the end effector of the robot arm and get data that can be useful for example, learning how to grasp hardware boxes. Point cloud in particular was shown to be to outperform other methods made based on RGB images or depth images, and so we directly used this one and we didn't use other methods. The other concept is human interventions. So when we have to work with dual arm robotic system, the action space and the state space of our problem are incredibly big, and with the state space becoming that big, also achieving a policy that works is more challenging. So in another work, they introduced this concept of human in the loop that basically consists in starting the training of the policy that we want to train, and then by just pressing the space mouses, the operator is basically able to control the movement of the robot, and in this way it can perform action directly during the training and substitute the action sample from the neural network to the one actually performed from for the operator. And in this way, you can basically correct small wrong behaviors of your policies and speed up the training. And as you can see from the graph here, from the plot here on the right, the red one is the number of interventions that we perform per episode. And as it goes on, the training, after a certain step, you don't need any interventions to make your policy work. And the number of successes, that is the blue line, just continues to grow. The other concept, okay. For the motion task, we introduced this concept of insight experience replay that was needed first to record the demonstration and then to improve the performances of the training. The principle behind insight experience replay is to make use basically of failed experiences, converting them into successes one. So for example, when recording the demonstration, we need to move the object to a certain point that is sampled randomly in the space, in a certain regional space. But it's obviously hard to know exactly where this point is if you cannot visualize it. So the principle behind this algorithm is just to move the box randomly to a point in the space, and then at the end of the episode, if you didn't arrive to success to the position where you wanted to go, you just recompute all the observation and all the action that you perform, considering the final position where you arrived as the goal. So in this way, you basically speed up the training because the agent still continues to learn from failed experiences, but you can basically take advantages of what you were doing. The other concept is residual reinforcement learning. Residual reinforcement learning is an advanced technique that basically makes use of the advantages of model-based controllers that are basically the efficiency with learning-based controllers that are more adaptable to changing circumstances. And in particular, when we use this kind of residual reinforcement learning, our policy is split in two parts. One that is a human design controller and one that is a learned controller that is learned online. And what we were doing was basically just substituting this term and giving as feed-forward term to the policy. In case of the motion, just the distance, so the direction along which the robot should move to perform the task. And in this way, the robot just had to learn the remaining, so to adapt to the changing circumstances, the possible problems that there are in the grasp, to properly perform the task that was needed to be performed. So now, going on, this is the setup that I used for the evaluation. as I mentioned before, you can see it on the left, there are two wrist cameras, one for each robot, from which we were taking data and converting them into point clouds. And then we used another camera to do the pose estimation of the boxes so that we can know the position and the orientation of the box in the scene. And during the training, we just used the box that you see here that is labeled as number 50. But during evaluation, in order to see how our policy were generalizing on boxes that were not shown during training, we took other 4 boxes with different sizes and shapes and weights also. And just to repeat it again, the real challenge of this problem is to basically obtain a policy that works when you have objects with very different conditions. So, for example, we realized that suction cup don't work very well when there is tape. So, if you have to grasp a box that is covered with tape, it's not that easy to achieve. Or if there are holes because you cannot grasp it properly. Or sometimes it might happen that you destroy your box during an evaluation and you have to use it later, and so you cannot use it properly. And yeah, so the policy grid needs to adapt to the real world characteristics of the object. And so, as I mentioned before, we trained some policies. Those are some evaluation that I recorded. On the left, there is the lift policy, and the task is to grab the box and lift it by 5 centimeters. So we are basically measuring how much it's going up. While on the right, the task is just to rotate this box. So we have to grasp it and then rotate it by 40 degrees. We just decided randomly, and we decided to rotate it around one of the axes. Then the other 2 policies that I trained are these 2. So on the left, you can see the combination of the lift and the rotation. So the task is to lift the box and then rotate it by a certain angle. And on the right, you have the policy that wants to move the box to a certain position in the space. So just position, not orientation. And this position is sampled at every episode. So during the evaluation also we were sampling different positions to test if our robot was generalizing enough these performances. And I obviously am not going to show videos for every box using every policy because it will take a bit longer. But I can show you quickly the overall results. So these are our performances of the policies. And just to make it easier to visualize for you, we have every task, and I just plotted the performance on this is on the scene box, so the one I used during training. And what you can see is that our simple baseline, that was a simple behavior train, is basically doing this job, but our learning policies are doing a bit better. And in particular, what we can notice is that policies that use visual augmentation have better performances. We didn't use visual augmentation just for the motion task because there was some hardware problem during the thesis, basically, so we just skip it. And we also used residual reinforcement learning just for this last task, so the motion task. And you can see that the performances are a bit better, but we were not using any additional visual information.
So what is RLPD?
It's the other algorithm. It's an algorithm. Like SAC is actor critic, RLPD is just the other algorithm.
Okay. Can you give us a little bit insight on why does the SAC for the lift task is worse in the behavior tree this time?
Yeah, I have to clarify one thing. So, okay, I recorded the evaluation during the overall period. I can also, can I answer in 2 slides? Because there is also partially the answer. But okay, the quick answer is that I recorded the evaluation during a different period, so the setup changed. So I have every time to retrain the policy from scratch. And sometimes I just didn't have the time to redo it again because it takes a bit of time. The reason that I will show later is that sometimes it just happens that just one arm is grasping the box and lifting it, but if not, the 2 robots together doing it. So the success rate is a bit lower sometimes, but like it's something you notice also here. And also like what I can maybe mention, because I didn't write in the other slide, is that those algorithms, so SAC, all of them were basically trained in 12 minutes. So the policy was evaluated after 12 minutes that it was training, and the other one with visual augmentation, they take a bit more time, and they took like roughly 1 hour and a half. So if also like, and also like since we were using different boxes, coping, for example, with boxes that are very small is more challenging than boxes that are much bigger. So even grasping sometimes is hard. And yeah, and then here there are the performances on and here there are the performances on the unseen boxes. So you can see that the results get a bit worse because we were not using obviously the same box that we were, so the conditions were basically different from the evaluation. And similarly, you can see where are the baseline, and you can see that some tasks still achieve very good performances, but some other no. They have worse performances, but as I said, like changing the condition and the shape basically of the box change also the results. Like if we probably differentiate by size, the performances are a bit similar. Sizes with respect to the box used during training. And okay, the other thing that I wanted to reply is that we also noted that sometimes it happens that the agent is just completing the task but not the way we are expecting it. So sometimes it was happening, for example, that the box was lifted by the threshold that we said, and it was grasped, but it was just grasped by one robot arm. So the task was still achieved in a certain sense, but not properly as we define it. Or either here on the right, the box was rotated at the correct angle, but it was not grasped at the end, so it was not triggering the success condition that we defined. So taking inspiration from another work, and in order to give a better overview of the performances of the policy, we defined some sub-successes that basically allow us to characterize even more the performances of our policies. And for example, I just show it for the motion, but I also have the data for all the other tasks in the background of my slides. So we define, for example, for the motion, here on the right you have the success rate, while on the left you have the motion sub-success. That basically means that the box arrived to the position where it was supposed to go. Like it's just what this success is checking. While on the right you have the success rate, and you can see that the box is actually capable of achieving even more than the standard algorithms, arriving more frequently to the correct position than one you actually see during considering just the success. So how we define the task. And similarly, so yeah, you see that it grows. Similarly, we can also have a look at the final distance of the box from the goal, and the success threshold was set at 5 centimeters. But if you look at the performances of the different policy, you see that learning-based method decrease this distance. So the final distance of the box tend to decrease with respect to the one that you see in using model-based controller. And yeah, so just to conclude, for this thesis, I trained the first online reinforcement learning policy for a dual-arm system operating with sanction cap and using point cloud visual inputs. And I also integrated for the first time, or at least to the best of my knowledge, the first time, insight experience replay and residual reinforcement learning in a pipeline that is trained using online reinforcement learning for manipulation. The limitation of our approach is, as I mentioned before, the fact that we used just one box for the training. So during training we didn't introduce more boxes, and this was due mostly to constraints that we had in our setup. And this also led to poor results on the unseen boxes, in particular when the sizes of the boxes changed a lot. And as future work, I would suggest to find a technique or a way to introduce more boxes during training in order to generalize even better the performances. And also, one thing that we realized, especially for the motion task, is that our library basically works well when the task is repetitive enough across the different episodes. So when the task is always to grab the box and lift it by 5 centimeters, but it doesn't work well when basically the task is more value. So when you have to move it to a point and then the other episode to another point, and is not sample efficient, then the training time tends to grow. And what I think would be worth to try is to use different reference frames to represent our observation space, and in this way to try to kind of improve the efficiency of the algorithm that we are using, giving data that are kind of normalized in certain sense. So this was the presentation of my thesis. Thank you very much for attending, and now I'm happy to reply to your questions.
Just to see if I understood correctly, you train one policy per task, right? It's not
Yes.
one single policy that does all the tasks.
No, it's one per task.
And the results you showed are in simulation?
No, it's
or in
online.
real
The
world?
training was also online.
Okay.
Wait. Maybe I can also close.
So you never used the simulator?
No, I'm not using at all. So if online reinforcement learning, if not
Okay.
using simulation at
Okay.
all. So what you saw here actually, I just close it because maybe it's faster. It doesn't respond.
No, yeah, but basically here you were evaluating and you were.
Yeah,
also
this was the evaluation. Yes.
Did you consider an online setup because you can do a lot more domain randomization and stuff and rapid training in simulation? Obviously,
Yeah.
in the real world, it's different. Would it have been possible to train some baseline power policy in sim and then use online?
Yeah,
learning?
this is also done in some tasks, but we try to go fully RL because we were using this library that allows to train. And you already have some kind of domain randomization because the box position is changing, like it's not the same every episode. Also, you have directly the noise of the measurement. So the problem was not probably the domain randomization because you have probably even more.
Okay.
The problem is more about the efficiency of the training. And maybe not close, I guess. So here, what I wanted to show, because probably it's easier. Like this video here was a training. So this was the training. It was not even, yes. This was already the training. So like when you see the arm moving, okay, here I was touching, but here I'm not touching anymore. And it was training. So it was every episode, it collect the data, it collect your transition, and then it basically update your network directly, everything will do. Yes.
Okay, thank you so much for the presentation. I can see it was a lot of work in dealing with kind of real world training and stuff like that. You presented 3 or 4 kind of components of the framework that you were using inside PH Replay, the human in the loop intervention, and the residual reinforcement learning in the real world. Maybe I'm missing a component. Maybe it was something about like the voxelization or the point clouds. Yeah, I remember there was
Yes,
right?
yes.
But then the question is, so what do you think? Like, what is the secret sauce? What do you think? Which component of this do you think is the one that is helping you more to achieve the level of success that you have? And which component do you think, like, if you had to choose 1 or 2 components of these to further improve the performance, which would be a component that you would say, if I fix a little bit more, if I work a little bit more on this part, maybe I can get better success?
So you mean like not using the same one but improving one of these?
Yeah, like, well, the first part of the question is, which one do you think is the most important one? And then which one do you think is the most promising one?
Okay. Let's say in the game changer, if you want to define it like that, were human interventions. Because it allows basically to train, okay, I didn't mention it, but in this work that I'm also citing here, they were taking more time than the one I was taking to achieve policies that were working. Like the one that you saw before, when I showed the CERN slides, they were training in like 3 hours. I basically did it in 1.5 hours, that is still a reasonable time, if you think about it. So this was something that really helped to improve the training, because you can really, you can basically fix all the wrong behavior that your policy has. So for example, if then the factor is not rotated properly, it cannot grasp, or stuff like this. And then the other thing that can help, in my opinion, so also, okay, the point cloud was helping a lot, but still it takes more time than just not using it. One thing that can help, but if the one I also mentioned in the final slide, was the definition of different reference frame to train the robot on, to train the policies.
I see. So you're just working better on the observation space.
Yes, because the problem is that with simple tasks you can really just record it once, like do one rollout basically when you like record the demonstration and then you train it and it works. But when you have more complex tasks, you need some more advanced techniques to make it efficient, like to make learning efficient in reasonable time. Because otherwise you have to let it run for 5 hours and it's taking a bit long.
What is the frame that you're using right now? Like, is that like object-centric frame or is it in the word frame?
No, it's in word frame. Actually, it's not exactly word frame, so it's end effector frame.
But there are two robots, and like, how does that work? Like,
Yeah, basically the way they were doing it. So I also still take inspiration from other work. They just put all the observation relative to the two end effectors, and then they fed it directly to the network.
Yeah, but these two end effectors are changing.
Yeah.
And if you have one end effector, I can imagine you can do it like relative to the end effector frame.
Yeah.
But if these two are changing, how do you define a coherent frame to define your?
That's why we would like to use another frame. Like what I mean is that it was done like that. We trusted it, and for some tasks it was still working. I will do it differently.
Okay.
This is your question. Okay. Because you have problems where, like the thing is that as soon as you have probably proprioceptive information, so just for example the force or the position of the end effector, it still works. But when you have additional data, it doesn't work much that well.
What frame do you think is the most promising to use for next?
I think at least for the okay, I have two ideas in my mind. The first one that I will also consider to do it was to use the box as reference frame. So take the center of the box as origin and pick also the orientation of the box as our main reference frame. The problem was that the measurement was very noisy, so we just didn't trust it. Another solution that will be probably needed in the motion task would be to use the goal position and just define also a goal orientation frame as reference, and then represent all your quantities or your observation with respect to this frame.
Yeah, I mean, thank you so much for the great presentation. I mean, maybe I'm not in a position for giving you a feedback, but I remember you mentioned something about like this method is like the first of doing something, right?
Yeah.
And are you 100% sure this is the first time you did this?
Yes, because in this paper they said they were the first to do it with RGB images, and there are no work with point cloud. Like, I mean, first with point cloud.
Okay.
And also, like, if also in site experience replay, I found some work that is using in-site experience replay, not for manipulation, but also is never done fully online. So usually it's training simulation and then the policy is deployed in the real world, but not done everything in the real world.
Okay. I mean, I would just be a little bit mindful if you say like this is first of doing something, because you don't really know whether this.
Yeah.
Right?
Yes, I to the best of my knowledge.
Yeah. Okay.
I wanted to ask about I didn't fully understand sort of, I guess, the observation space and the actor critic setup. So is the observation space being given like the joint and the point cloud information for both robots at the same time, and then a centralized controller is then a centralized policy is generated, or are these two independent robots that are only given their own observation spaces?
So your question is basically if the observation space, like if there are two observation spaces or just one?
Yes.
Like
Like, for
just
example,
one?
in a mobile manipulator case, you might have two robots that are
No,
not
it's
communicating,
just
but in a
one
factory setup.
observation. It's
Okay.
one observation space, and so you have the space for your like the end effector position and effector orientation,
Okay.
and then you just have some more layer where you directly first you have a decoder, so you pass the data through a decoder, you reduce the dimension, and then you feed it to the network.
Do you think? Sorry.
There's one network.
There is just one network.
Do you think potentially that limits the application to these more factory rigid manipulator setups where you can actually reliably share the information between them rather than these more maybe networked setups between different robots that maybe they're not rigidly in the same place all the time? Do you think there's a limitation there? Like if you were to try and adapt this method to mobile robotic arms, would it work the same way? Or
Okay, my guess is it will, if that computationally speaking, maybe it will be a bit worse than just using one, because then you have two networks, right? So you have to complete that. Like if you want to do it in simulation, no, because it's just done online. But if you want to do it online, then probably it's a problem, because you need something very powerful to do it. And also you need to share the data, you need to make sure that the latency doesn't ruin your data. You have the correct data at the correct time step.
Okay. But you definitely need a shared observation space for this to work.
Yeah.
I have a question.
Yes.
So, there's another master thesis from our own team, is concurrent, that's doing similar stuff on one single arm. So what do you see, like the single arm residual reinforcement learning from?
Which one is it?
Yes. Yes. So how would you compare your work with his? And what's the advantage and what's the extra challenge that's brought forward by this dual arm system?
Okay, so definitely using a dual arm setup is much harder because you have to control two robots at the same time. So, for example, you have to make sure that you don't have collision. That is something important. So here in the backend there is an algorithm that checks every time step that the robots are not getting into collision. And the other thing is that, for example, the observation space, you have to use two different cameras. If you just have one robot arm, you can just use one camera and fuse the measurements into one. And so yeah, you have less data, so you have less, also the observation space is smaller. And then the other challenges when using two arms, okay, record the demonstration is much harder, I can confirm, also because they are rotated, so you have to kind of move the space mouse knowing which robot is which one and where this will go if you move it this way. And but like if you just are talking about residual reinforcement learning, I think it's kind of similar. In his thesis, probably it was just a bit easier for him to tune the initial position of the arm with respect to the box position. For me, it's a bit much harder because I have to like give a relative position to the center. And also, he was doing it in a it was in. I am giving directly a goal position, so I'm taking the distance from the goal to the box and give it this direction. For him, it was a bit different. I think he was just defining a point and says move toward this point. And it was always the same. Like in mine, it's variating this point. That was the opposite. So also the action is different for every action.
Because from your experimental results, you showed a success thing, right? So it's basically, I see like a single arm, even if you're using two, a single arm can take you quite far. By doing this reorientation, rotation stuff. So I'm a little bit skeptical about, like why do we really need two arm? Because in the end, all of your two robots are facing down the indefactor and they're just operating like playing Tai Chi all the time. But I would be excited to see, like, for example, more spatial reorientation, because that's where really like dual arm really shines. For example, you're trying to pick up a really heavy IKEA package. What you're trying to do is like you grab and then you use one arm to pivot and the other one arm to kind of really, apply the force.
That also was one, like the one where you have to lift and.
So do you see this framework has hope or has any shine any lights on training our policy for tasks like that, but not only just like planar orientation?
No, I mean that's also why we try to do it, and it works. So yes, definitely, it's something that can be done. It was more just like we started with simple stuff to see, okay, we can do simple stuff, then we just try to do some more complex thing. And the advantage of having two arms is basically that you can lift objects that are much heavier, basically, and like this is the advantage. And and bigger, heavier and bigger. There was your question.
Yeah, so evaluation in the real world is difficult, right?
Yes.
Just after training, after all the effort you put on training, then evaluating things in the real world is just time consuming, it's very difficult, right? You change the setup and then the performance changes, right?
Yeah.
So if you had a good friend that was continuing with this project, what advice or feedback you give to this person to perform evaluation in the real world? Like, what are the things that you would have liked to do differently, and what are the things that you probably didn't have time to do?
My single advice would be to like spend some time in the beginning to see, for example, to consider which configuration is better to manipulate, because we choose this one with the two robots in front, but for example you can also put them on the same side of the table and move it, and you can also achieve different motion in this way. And so first choose the configuration, and then try to make sure that you don't have to move during the 6 months of the thesis.
Maybe just as a follow-up question, right?
Yeah.
Like, in the real world, things are going to change. You're going to have to move things one way or another, and it's unfortunate like that for a master thesis project, things have to move. But if you want to make this work in the real world, you need to be able to figure out how to make it work, even if things change a little bit, right?
Yeah.
So, what do you think would be like the strategy to be able to make it work, even if things change a little bit? Not drastically, but at least a little bit.
Yeah, that's why I mentioned the thing about the different frame for the observation, because in this way you can kind of be independent to where your robots are. That's why I mentioned it.
Sure. The frames, I think, could definitely help. But do you think there were other things that were limiting you? For instance, the policy representation. Do you think that the type of neural network that you were using to represent your controller is kind of the way to go? Do you think you should use something more sophisticated? Do you think? So, maybe this way. What do you think about trying to use diffusion policies, right? Like, diffusion policies have shown great results, and they also have limitations and potentials, like the amount of data you have to collect, but at least it seems they are a little bit more robust to certain changes, right? But then
that's definitely something to try.
Okay.
Yeah. I mean, I just work with this one, so I didn't consider other approaches. That is worth, because you have to still compare what are the performances with respect to other. But I obviously didn't work with them, so I don't know which are the challenges that then you have. Because maybe, like for example, you can also use imitation learning, but then you have to collect way more data than the one I was collecting. Like I was just using 20 demonstration. I also tried to use behavioral cloning that requires still quite a bit of demonstration, but it's faster to be trained, but it was not working. So maybe there was still something wrong from my side, but it's all like I cannot really give you insight because I mostly work on this one.
Sure, fair enough. Thank you.
A final question. You applied RRL to only the motion policy. Do you think it's also helpful for the other 3?
I mean, maybe yes. You have to obviously define it in a different way, but yes, it can help. Because in the end, like you can just use the command that you use for a behavior tree, and just change, like use the command as the feed-forward action, and then just learn the differences of the
Then, if there's no other questions, thank you again.